Hey guys, it's Arjun from Wizards.exe here, and we're going to be going over motors today.
Please like and subscribe.
And so, what we're going to start off with, I'm going to have a few people to thank. So Pankaj Oberoi, Ishan Oberoi, and Tom Milnes /FRC2199. I used them. They're pretty big help for making this presentation. And so I'm going to go into the outline. So for our outline, we're going to go over the FTC legal motors and servo motor and motors versus servos. And then we're also going to go into like torque and speed, all the cabling needed for motors. And finally, we're going to end off with motor and servo mounting. And so the first thing we're going to start off with is a bare motor. And so a bare motor has a few parts, and it's really, really fast. So you can see it's about 100 revolutions per second. And so I have one right here that I'm just going to show. And so you can see it's pretty short. Doesn't look like any motors you've seen for FTC if you have seen any before. And so the little black thing on the back right here is what's an encoder, and so that's essentially a rotation sensor.
So bare motor doesn't have a gearbox, is that what it means?
Yeah, it does not have a gearbox.
Okay.
Yeah.
And also, so if any motor knows basically how many rotations it did, then what's the point of a stepper motor?
Stepper motor is a different type of motor. So it works in a different way. We use DC motors in FTC.
Yeah, I know, stepper motors.
So stepper motors work in a different way. I'm not completely sure how they work.
So all the motors work on DC?
Yeah, all of these FTC motors are DC motors. Gotcha. They're all, and so yeah, that brings up another point. All of the bare motors in FTC are essentially the same thing. So even though they might advertise different specs, like different RPM, different torque, they're all essentially the same. If they're the same, most of them are the same. Yeah, there's a few outliers which I'll get into, but yeah. So then the next thing. Okay, so yeah, gearbox. So on the motor, so it goes at 100 revolutions per second. And if you saw a drivetrain go that fast, you would obviously, it wouldn't work because it goes so fast. So you get these things called gearboxes, and you can see that right there. So the parts of a motor you're going to see are, there's the output shaft on the top. You can see my cursor's up there. There's the gearbox, then there's the motor. And finally, there's the encoder, which is on the back, which is usually, it's essentially an encoder case. And so I have a few different gearboxes here. And so you can see this is generally what a gearbox is going to look like. It's fine. So you can see there's a few of that's what a gearbox looks like. And so they can have different output shafts. So like this one has a hexagonal shaft on it. And they come in a few different forms. So you can see like on the PowerPoint slide, I have a few of the other types over on the left. And so if you're curious to see what the inside of a gearbox looks like, there's a lot of grease. It's very greasy.
Can you technically change out gearboxes for motors?
Yes, you can. You can change them out. So most gearboxes can be changed out. So they have, yeah, so most gearboxes can be changed out. And so again, gearboxes go on the end of the motor, and most of them are compatible with most other motors. And so we're going to go to the next slide. And so there's a bunch of different common motors that are used with different gearboxes. So we're going to go over basically almost every FTC legal DC motor. And so again, important notes, the bare motor is essentially the same, so performance won't vary much. There are two types of gearboxes, essentially. There are Spur gearboxes and Orbital gearboxes. And so the main difference between them is that Spur gearboxes and Orbital gearboxes have their shaft in the middle, at least for mounting, you can see, while Spur gearboxes have them offset. Yeah, so you guys got that? Cool. And yeah, so we're going to start off with the Tetrax Tornado motor. I don't have one on me, but a few things to note is that it has a 37mm diameter gearbox, and the output shaft is a 6mm D shaft. So it starts off, it's stock with a 60-to-1 gearbox, but then you can also replace the gearbox for a 20-to-1 reduction ratio or a 40-to-1 reduction ratio. But again, you have to buy those separately. And so it's in the Tetrax FTC kit as of now, which is why you're going to see many teams use it. But other than that, it's not very commonly used, as it's a fairly new release. It was released pretty recently, as opposed to the Andy Mark Neverest, which are essentially the same thing, but were released much longer ago, so more teams have them. And so
all the new teams, because like most new teams buy a Tetrax kit to start off, they'll have them?
Yeah, so teams that buy a Tetrax kit will have them usually.
Okay.
And so, yeah, there's the Andy Mark Neverest gear motors. And so, again, the Tornadoes were Spur gear motors. These are also Spur gearbox motors. They're essentially the same dimensions as a Tornado with the 37mm Spur gearbox, and it has a 6mm output shaft. But they sell, that's not it.
Oh.
So they sell 40-to-1, 60-to-1 gearboxes for the Spur variant, but they also used to sell a 20-to-1 variant, which is faster. No, I have all three right here. So, Dira, yeah. So, you can see I have all three here. They're all essentially the same dimensions, so you can see that the lengths of everything are the same. So there's essentially no difference except for the gear reduction. No difference on the outside of the motor.
And for just a raw motor, what kind of ratio does it have? 40 to...
Raw motor, bare motor has none.
Oh, none? Just...
Yeah.
Okay.
A bare motor has no ratio. And so one thing... yeah, there's no internal gears on a bare motor as far as I know.
So how much torque does it have usually, just a bare motor?
I'll get to that later.
Okay.
Yeah, so these Neverest motors, they actually have an attached cable. Same with the Tornadoes. So you can see the cable is attached to the motor. So you can't replace this. If you ever need to replace a motor, you have to also replace some of the wiring. Okay, so there's also the GoBuild 5201 series Spur gear motor. It's, again, essentially the same as the Neverest motor and the Tornado, except it has different gear ratios. So it has the 25.83-to-1 and the 53.475-to-1 gear ratio. Those are the two options. And so this was released at the beginning of last season, Rover Ruckus season. So they're fairly new, and I haven't really seen any teams use them in competition. And the other main difference is it uses bullet connectors. So you can see those little things right there. Those are called bullet connectors.
Do you have like a bullet connector?
They're yeah, so you can do that. I'll get into that later. And so they have 3.5mm bullet connectors on them. Okay?
Why are the ratios so weird?
I don't know.
Okay.
Yeah, so this is a GoBuild thing. And so the last Spur gear motor is the Rev HD Hex Motors. And so they sell a Spur gear motor and a Planetary with most. And so you can see on the front of these, I don't have one on me right now, but there's both the normal, so most of these Spur gear motors that are 37mm have their own mounting pattern. But then the HD Hex, in addition, also has the Rev mounting pattern, the 16mm Rev motion pattern. So it's also compatible with Rev. And so what's really different about these HD Hex motors, you can see the back of them has connectors for both power and encoder. So you can see right there, you can take a look at the back of the motor. And so that's Spur, you have power for both the motor and encoder. You guys see that? Now we're gonna get into Planetary. So one thing you need to watch out for is you're gonna see manufacturers use the words Planetary and Orbital essentially interchangeably. So I believe from some manufacturers it'll be called a planetary gearbox, but from others it's going to be called an orbital gearbox. So just be aware of that. And so you can see an image here of a planetary gear set. And so they're stronger than than Spur gear sets. And yeah, there's not much. So the planet gears are the idler gears. There's the sun gear, and then there's also going to be the ring gear. So yeah, another thing to be aware of is that a lot of orbital motors that claim they're a 20-to-1 gearbox are actually a 19.2-to-1 gearbox, and so they're going to say that. So this is just something they approximate just to make it easier for teams to use, because it's a lot easier to do math with a 20 than 19.2. And so this happens for a few different orbital gearboxes, but that's just something to be aware of. You just should check what the manufacturer says the gear ratio is, and not what they say in the title. And so that starts us off with the AndyMark Orbital Neverest Orbital, and so they have two motors they make. So they make a 3.7 and a 19.2-to-1, which they call the Orbital 20. Again, but it's a 19.2-to-1. And so they both have a 6mm output shaft. They have a 37mm gearbox, and they both have an attached power cable, just like the other AndyMark ones, because they're the same bare motor. And so you can see one difference is that
and they also have a sensor, right?
They all have encoders.
Okay, yeah, encoders.
They have slightly different length gearboxes, so that's something to be aware of. So if you build something with a Orbital 3.7, which has the shorter gearbox, be aware that you should check if it works with a Orbital 20, which is what they call it, just because that could happen. So yeah, you can kind of see that on this camera too, I think. Yeah, you can see that a little bit on here, is that they do have slightly different gearboxes.
So theoretically, the fastest motor you can get is a raw motor.
Yeah, so the fastest legal motor in FTC is a bare motor.
So do most of the bare motors do 100 RPM?
It varies, so motor specs vary, essentially.
Okay.
So, but they're all essentially the same. Like, if you have an AndyMark raw motor, bare motor, you can switch it out with the Rev bare motor, and you shouldn't really see that much of a difference in performance. Okay. And so there's also the Rev HD Hex orbital motors. What is that? Did anybody give me? Oh, here it is. We have a lot of motors out here, and so it has a 5mm hex output shaft instead of the 6mm D shaft that literally every other motor really uses, except for the Rev ones. And so one thing to notice about these Rev motors is that they have an extra long output shaft. That's to make it a little bit more compatible with the Rev building system. So here, if you look at a Rev motor versus a Neverest motor, the Rev orbital motor is going to have a much longer output shaft. You can see that. That's just because of how the Rev ecosystem works. But some of the older Rev HD Hex motors, I have a Spur gear motor here, still have the short standard output shaft which is, I believe, 26mm output shaft instead of a 40mm output shaft. And again, the Rev HD Hex motors do have the nice connectors on the back. So we're going to get into the next one. These are somewhat of an outlier. So they were released the summer before this season, so before Rover Ruckus season. And so they're the GoBuild a Yellow Jacket motors. And so they have a 32mm orbital gearbox, which is different than normal 37mm orbital gearbox. And so instead of the standard, which have M3 threads on the face of the gearbox in that standard pattern, and so there are two standard patterns. There's really one for the 37mm Spur and one for the orbital gearboxes. They have the GoBuild a pattern in M4 threads on the front of the gearbox, and so that makes it a little bit easier to interface with GoBuild a parts. They have a 6mm output D shaft, and there are a ton of gearboxes they offer, from 188-to-1 to 3.7-to-1. So one thing they actually do say is it is not recommended you stall the 188-to-1 because if you're able to stall it, you're probably going to end up bending your shaft on the motor.
Yeah, it's logic.
Yeah.
What is?
And so GoBuild is like does not make FTC legal motors technically. So you're going to see here, it actually has the modern robotics sticker on it.
What does stall mean?
Stall means you stop it. You put so much force it can't move anymore.
How?
How?
Like, how would you? Okay.
If I have
that would mess with. The
yeah. So these have these have an attached power cable with 3.5mm bullet connectors.
And I just want to be sure the gearboxes don't have like an over torque limiter or something like that.
No. So you can see those 3.5mm bullet connectors there. And so one other thing to note is that the gearboxes definitely do vary in length. So you can see I have 3 different motors. So 2 of them are very similar, but then one of them is most definitely longer than the other 2. And so these are 3 of the different gearbox options that they offer.
Does the longer gearbox usually mean a higher gear ratio?
Yes, because it requires more stages of gears to get to the final output.
Okay.
And so now we're going to get to 2 motors that are not commonly used in FTC at all anymore. And so that's the Tetrax Max motor and the Matrix motor. So we're going to start off with the Tetrax Max motor. And so these are not very commonly used as they were replaced by the Tornado motor. They're much smaller than the Neverest motor, and they have detachable connections. So I'll show that now. So you can see they are much smaller than the Neverest motors. You can see that. And they actually don't have an attached encoder to them. And so you see the power connector on the back is actually detachable. And so this wasn't the best for them. You can see you can actually take that off. So teams would end up duct taping them down because you already have another connector for the motor. But so that's nice, except it's not. The connector doesn't have any sort of lock on it. For getting an encoder, you have to buy a separate encoder, which you have to install. So you can see the one with the black enclosing is the one with an encoder. The other one was without, and you have to manually install the encoder. So it's a little hard to use. And so the main reason you don't see teams use it, so it's a rarity to see them used. But if you do see it used, the main reason is probably for its size or weight. Yes.
So, you know how earlier you talked about a motor that had an encoder, had also, like, it was unusual because it had an encoder output?
They all have encoder outputs.
Okay, sorry, because I thought I heard you.
They have different cabling.
So that doesn't have an encoder in it?
No. These were in the original Tetrax kit. So these were, from what I'm fairly sure these were used since the beginning of like FTC. Or sometime around then, and then they've just been and then they started getting replaced by more modern motors like the Neverest motors.
Okay.
Yeah, and so the next motor I'm going to go over is the Matrix motor, and so the Matrix 12-volt motor is again not commonly used, as Matrix isn't commonly used in FTC anymore. And so you're not going to see this used, really. It's a rarity. Like, I don't think I've seen a single one be used last season. And so it comes with its own mounting bracket. So it has some it's much weirder. It's a different diameter, and it's a much smaller motor. It has a built-in encoder and power cable. So you can see it has both wires built in. So if you have to replace the motor, you have to redo wiring for both the encoder and power, as opposed to just the power cable. It has options for a 4mm and 6mm D shaft output. So I have the 4mm version right here. And it's just different. It's much lighter, so you would use this if you want something to be much lighter than the other motors. Or you just really want that form factor. And so that's most of the motors. The final motor we're going to go over is the Core Hex motor.
Is it a servo or a motor?
It's a motor. It's classified as an FTC motor. An FTC is a motor. And so it has the 16mm hole pattern for mounting, which is the Rev pattern. It has a female 5mm hex shaft, so output, meaning you insert your own shaft. So you can see at the bottom right, you see that little, those shafts. You can put your own shaft into the core hex motor. So it's known to break under shock, so you probably don't want to put this in any high shock like situations. Like if you have it suddenly jerk, if you have it jerk into something, the gears might grind. It's about half the weight of the other generally used motors, and it uses a different base motor, and it has connectors on the back. So I have one that I've taken apart here, so let me just quickly pop the top off of it so you can see.
And what gear ratio is it?
I believe it's a 72:1, but it's a different base motor. So you can see here I have the core hex motor, and so it has this much different base motor, and it connects through bevel gears to another gear ratio here, culminating in that 5mm hex output. So another thing I need to show is actually the backs of these motors. So you'll be able to tell if between different, some of these core hex motors will have a little casing around the power connector. Some of them won't. So let me just switch views. You can see the difference with the ones with the little casing and without. So you can see there's a little square-shaped casing. And so that's, so the one with the casing is actually a newer model of the motor, while these ones without the casing are much older versions of the motor. And so as far as I know, there aren't very many differences between them, but that's something to be aware of. Yes.
Do people use this when they need, like, because of the fact that you can have as long a shaft as you want?
Yeah, so it's essentially the form factor is great sometimes. Like, say you want a motor to be running along a channel. This is great if you don't want to use bevel gears, because you could run one of these Never-S motors or any of the other FTC legal motors, but then you'd have to use some sort of bevel gear set in order to, if you wanted the output shaft to be perpendicular to the motor.
But this motor is not as powerful?
Yeah, it's not as powerful. It doesn't have as much torque.
So it's not a motor that would be used in drive.
Yeah.
So some people do use it in drivetrain, but it's not recommended.
Okay.
Yes.
I guess when the assembly, you can have it perpendicular, you can also have it go in both directions.
Yeah. So there's advantages to the core hex motor. There's also disadvantages and times when not to use the core hex motor.
So do people like use this for like running like intakes and stuff?
Yeah.
Okay.
So sometimes you'll see it used for running intakes. Yeah, but intakes usually you'll see somebody run a Never-S motor or a servo motor, which I can get into. But next, let's see what's next. So we're gonna get into cabling, and so there's two sets of wires that connect to the motors. There's the power wires, which are the red and black wires, and then there's the encoder wires, which are for the rotation sensor. And so sometimes you'll just not want to plug an encoder into your motor just because you don't need to use it. But I'm going to get into both of these and the connectors used. And so on the Rev Expansion Hub, which is what we use in FTC, we have this thing called a 2-pin JST. We have this thing called a 2-pin JST VH connector. And so that's what's used for motors. And so I have some specifications down there, which were taken from the Rev Expansion Hub guide. And so on the Rev HD Hex and core hex motors, you have the 2-pin JST VH connector. So where did I put them? So you can see they look essentially identical to what's used on the Expansion Hub. It's the same connector. And so you can see Rev sells a few different things. So they sell pre-made wires, which are much better than what we can crimp by hand here. So it's recommended you buy those. But then they also sell these JST VH extension cables, extension boards, which just connect two wires. They're like a coupler, essentially. And yeah, so you just use a JST VH to JST VH cable. Everybody good on that? Okay, so then there's the Andy Mark Neverest / Tetrax Tornado power. Again, I'm not going to get into the Tetrax Max motor or the matrix motor and how to use it, as that's not really going to help you. So these motors come with Anderson power pole power connectors. So they're really nice connectors. It's a very robust connector. And so you can just use an Anderson power pole to JST VH connector. And so I'm just going to show power pole right here. You can see that. So you can reverse them if you really need to, but they're just really nice connectors. They're essentially the industry standard. Okay, so you can crimp power pole cables also. It's possible to do that. So we crimp our power poles most of the time. And then there's the GoBuild Yellow Jackets, which are the oddball, as they have the 3.5 millimeter bullet connectors. And so GoBuild does sell adapters for the bullet connectors to the JST VH, and they sell bullet connector extensions. But on our team, what we would end up doing is we would just cut off the bullet connectors and crimp on power pole wires. So now we're going to get back into encoders, and so we're going to get what's an encoder, how does it work, and how do we wire it. This is going to be fairly basic on encoders. We're not going to get super in-depth on these. And so an encoder, the dictionary definition is essentially an encoder is anything that converts information from one format into another. But in FTC and in this presentation, we generally refer to rotary encoders. And so there are two main types of rotary encoders, which are ones that like measure stuff in 360-degree rotation. And so there's absolute and relative. So what an absolute encoder is, no matter if you turn it off, turn it on, or turn it off again, it's always going to return one precise angle of rotation. So it maintains position even if power is removed. And so the shaft and the encoder are bound together when they're assembled. So these are often going to be used in things, think about a swerve drivetrain, where you always want to know where the wheel pods are, even if you stop them and don't align them correctly. Or if you have some sort of arm that every time you restart, you want it to keep the position so that even if you don't completely reset the arm or reset your robot, it's still going to know where it is. And so this could be like on the steering on a car, or possibly like a volume knob. Yeah. And so usually these only have 360 degrees of like feedback, but they can still rotate indefinitely. Like they can continuously rotate usually. But there are some. But relative encoders are referred to as incremental control encoders, and these are used on our motors in FTC, usually. You can get custom encoders probably, but you can get custom absolute encoders, but it's on the motors built in, you get relative encoders. And so essentially, they provide pulses when the motor is rotating, and so they essentially tell you, you've rotated like 30 degrees since you started, you've rotated 60 degrees since you've started. You can zero them out whenever you want to. Yeah. So they get zeroed out whenever you power on or power off. Everybody got good about that? Okay. So there are two ways that these relative encoders will work. There's optical and magnetic. And so optical essentially will have a disc with markings, shine a light on that disc, detect when the marking changes, and then it'll know where it is. And so this is sensitive to dust, to dirt, etc. And so then there's magnetic, which is what's used on our encoders. And so essentially what they do is they have a magnetic disc, and they use this Hall effect sensor, which essentially senses the magnetic fields to determine when it's changing, and then they know how much it's changed based on that. And so I actually do have a encoder without the disc on it. Right here you can see once you take off the encoder casing, which is the little piece of plastic, you can see the encoder, and you can actually see the encoder disc. So this one we took off the disc, but you'll be able to see that you can see both of those Hall effect sensors. Which are going to be at 90 degrees. I have another diagram here.
So does the magnetic sensor work on like the same principle as like a speedometer on a bike, where it like senses it every time the magnet on the wheel goes around? It's a bit more accurate.
So look up there, so you can see how there's the magnet, the disc has north, south, north, south, north, south, north, south. Yeah, and so it detects when it's changing from north to south.
Oh, okay.
the north and south pole of the magnet. And so that's directly from the Rev guide. And so we have 12-pole quadrature sensors is the technical term. And so
any motors use opticals? Or?
none of these that we're going over, as far as I know, use optical, just because it's sensitive to dust, dirt, grime. That can get into your FTC robot, or yeah, that can get into your encoder pretty easily. And so if you want to read a little bit more, like how does the signal work, what does it look like, or any more depth, I recommend looking at the encoder guide from Rev. It's really in-depth on encoders, and it's a really good guide. Good? And so now I'm going to get into the encoder compatibility. So the old control system, the modern robotics control system, used 5-volt logic. So all of your encoders needed to be able to run off of 5 volts. But then the Rev Expansion Hub came around, and it runs off of 3.3-volt logic. So most motors at the time still used 5-volt logic. So Rev released a little piece of electronics called a level shifter to convert those 5-volt, the 5-volt logic to 3.3-volt logic. And so most companies, basically every company, AndyMark, GoBuild, and Tetrax, all say that their motors are incompatible without level shifters, just directly to the Rev Hub. But with older motors, you're still going to need to use that level shifter. So the encoder connector on Expansion Hub is a 4-pin JST-PH connector. And so it's the same connector that's also used for sensor ports on the Rev Expansion Hub.
But isn't the encoder one next to the motor? There's like 2 ports right next to each other.
Yeah, so that's what plugs into the Rev Expansion Hub, because you have 2 ports on the Rev Hub for every motor.
Yeah.
And so for Rev HD Hex and Core Hex, again, you have the 4-pin JST-PH. So all you need to do is use a JST-PH to JST-PH wire. You don't need to use any fancy compatibility cables, nothing. It's very simple. So if you want to see that on a Core Hex or a Rev HD Hex motor, there you go. So you can take a look at that. My lighting's not perfect. I'm not going to get into the matrix motor for this.
It's just one wire.
So it's 4 wires, but yeah, it comes in the form factor of 1 wire. It's 4 separate channels. So now we're going to get into the Tetrax, Tornado, and GoBuild motors. And so these have a 4-pin JST-XH connector, which is still keyed, but it's a different wire. And so the encoders on these 2 motors are compatible with both 3.3 volts and 5 volts. So both of these companies sell a cable converting the JST-XH to JST-PH. So just a JST-XH to JST-PH wire. So it's still really simple, 1-wire solution. Yeah. Now we're going to get into the AndyMark Neverest. And so the newer Neverests are essentially compatible with both, with the Rev Expansion Hub, like with 3.3 volt logic, where you just use the same as the previous slide. But some of the older ones only work on 5 volt logic. And so they use a 4-pin JST-XH connector. And so you can see they have a little wiring rig right there where you can click on that link if you want to see it. Has to use a level shifter, which is what that little thing in the middle is. That board in the middle is a level shifter. And so I've talked with Greg from Rev, and essentially what they say is the AndyMark encoders have changed over time. So some of the older encoders aren't going to be compatible directly with the Rev Hub and have to use a level shifter, while some of the newer encoders are going to be compatible with them. And so there's not really a way you can really tell, so you have to test out your motor to check if it's compatible.
How do you test it?
You just try and read the encoder value. You just run it, and
this wiring is just for the encoder, right?
Yeah.
Okay.
That's for the encoder, and then you still have your separate motor power. And so there's a little summary. Rev motors made by Rev are really easy. Those are the easiest because Rev makes the expansion hub. Most other will just require a 1 cable solution, just an adapter cable. And so one thing is most top teams will actually replace the bare motor with an HD Hex bare motor, because the wiring on that HD Hex is much easier to use. And in any repair situation, if your motor breaks, you're going to have to deal with the power cable on most of these motors, except for the HD Hex motor, where you can disconnect the power cable on the motor itself, so you don't have to undo any wiring, really, whenever you make a repair. Got that? Okay. So now we're going to get into torque and speed, and so this is the hard part where you have to grasp some concept, which if you're not familiar with is pretty hard to grasp. And so we're going to start off with speed, and so speed is essentially how fast something is moving or rotating. And usually in FTC, we're going to refer to angular speed, and we usually refer to RPM, which is revolutions per minute. That's the main unit that we use. But then sometimes you'll also see people use revolutions per second. If the RPM is really, really high, it's often easier to deal with revolutions per second. And then torque. So torque is the hardest definition you're going to have to learn in this presentation. And so the dictionary definition for torque is a twisting force that tends to cause rotation. So it's a twisting force. It's rotary, which it rotates. And so the common units for this are going to be ounce, inches, and Newton meters. So ounce, inches, and Newton. So we use ounce, inches. That's just what we've done on our team. And so essentially what it's saying is you have a mass like X inches away from the pivot point, which weighs X, which weighs like Y. And then torque is the amount of like the rotation required to rotate that around. So say I put this servo on the end. So I'm just going to make up a number here. This is definitely not right, but this servo probably weighs around 10 ounces. And so if I put it right next to the pivot point, like 2 inches away, it's much easier to rotate, meaning it requires less torque. But if I put it 12 inches, a foot away, it requires a lot more torque to rotate.
So torque is the force that I'm applying at the end to push it up.
Torque is the force you apply at the pivot point, essentially.
At the pivot point to move it up.
So you
to move it around.
The mass.
So when you said ounce, inches, where did the inches come from?
Inches away from the pivot point.
Wait, and the torque is stall torque? Or?
So stall torque is what you're often going to get, but I'll get into that later.
Okay, Arjun, hold on. Doesn't the force depend on how much you want to move?
Yeah, torque.
Where is that?
No, it doesn't depend on how much you want to use.
Work.
Okay.
Yeah,
So it is
that's
just
work.
the force required to move this
Yeah.
up, or rotation.
So it's the weight of it times the distance from the pivot point?
Yeah.
Okay.
The weight of, and so you could take into account like the weight of this ruler, but that's called moment of inertia. That's a little bit more complex. And in FTC, we generally don't work with this because, so in FTC, we take the stall torque and then essentially have it, so double the requirement. So if this is like 10 ounces, we'll do our calculations for if it's 20 ounces, just so that we're always within a margin of error. If the battery's bad, you never have it fail. There's a linear relationship between speed and torque. So that means if you gear it so that you get more speed, your torque is going to go down linearly. But then when you go for power, power is just torque times angular speed. And so power, that's what the curve looks like for when you change the torque. That's what the power curve looks like. Now current draw is going to increase when you're using up more torque. So that's what, yeah. When you need more torque, the current draw has to increase. And then efficiency, motors are never 100% efficient. That's stuff that happens in theoretical physics. We are actually building stuff. We're not just designing something to be theoretically correct. So that's the efficiency. So the efficiency is that final, the efficiency is this red curve, I believe, right here. Yeah, the efficiency, and so Vex did some really good testing on Neverest motors and all of the FRC legal motors a few years ago. But now this is a bare Neverest motor that they've done, but a lot of newer motors they haven't done testing for But you can see this is what you call a motor curve, and this gives you all the specs of a motor and its performance. So you can see the efficiency on this is going to be a lot more, the motor is going to be the most efficient when you're around like 70-80% of the speed. But then you can see it uses the most power when you're at like 50% of the speed. So this is what you call an efficiency curve, the motor curve. And now Rev also gave a theoretical motor curve. Yes?
Why did the efficiency drop so suddenly?
That's just how it works. I'm not completely sure on that.
Okay.
So that's something you'll have to research into. Now this is with the 40-to-1 gearbox. And so remember that gearboxes add inefficiencies. So what's interesting is this goes up to, this is theoretical, I think. They haven't provided any other specs on how they got this motor curve. But it's efficient at much lower torques when you're at low torque. But one thing I'm fairly sure is that the x-axis on these VEX motor testing is speed, while the x-axis on the Rev motor testing is Newton meter. So you'd have to adapt this to take a look at it.
Ounce per inches. Newtons per meter sounds so.
We use ounce inches here, David. And yeah. And so that's the takeaways. So the Rev HD Hex motor had a much lower max efficiency than the Bare Neverest, I think. Yeah, so you can see the efficiency here is about 43%, while the Bare Neverest had 60%, so gearboxes do lower efficiency. Got it?
Mm-hmm.
And so this is just a test that VEX did another test. I'm not completely sure how you'll interpret this, but this is for reference if you're interested. Now we're going to get into what a servo is. And so a servo is generally less powerful than a motor, meaning like torque times speed is going to be less than the motor, at least in FTC purposes. And it has a much different form factor. And so there are two main types that are FTC legal. There's regular servos and continuous rotation. So first I'm just going to give a little demo of the difference. So here I have a Rev servo. And so you can see that when I turn this on and hit test, this is currently in regular servo mode, meaning that it can only it can rotate only X degrees. I don't know how many it is. I believe it's 270 for the Rev servo, but you have to configure that. You have to program that. So these can only go, you get position feedback on it, but again, you can't rotate all 360 degrees.
Why?
Why? That's how servos work. It's just how it's built. They have a built-in stop.
Is that because there's no way you can't encode a servo?
I'm not completely sure on that, but you can get encoders on servos. So now there's also continuous rotation servo, where all you can do is tell it which direction to go in and how much speed, essentially. So that you get 360 degrees, but you don't get position feedback most of the time. So,
And servos are more accurate than motors.
I'm not sure about that. That's something someone would have to research, but nobody has. As far as I know, there's no research on that for FTC. And so what makes an FTC servo legal? So it has to be able to operate on 6 volts. It has to be 3-wire servos. So there's power, there's ground, and then there's a PWM, which is essentially an analog. It's PWM is actually, it goes on, off really, really quickly. Like, I don't know how to say how fast it goes, but it goes very, very fast. And then it's much more than hertz. And then depending on how fast it goes, that's what the signal the servo picks up.
I think it stands for pulse width modulation.
Yeah, it is PWM, pulse width modulation.
So then how many volts does a regular motor use again?
Those use 12.
Okay.
And so then there's also the one exception of a VEX 393 motor with the motor controller 29. I am going to get into that.
And do the servos have like a special input on the...
So motors have the 2-wire input. Servos have the servos have ports on the bottom, so you can use Vera, can you put that down? You can put you can have 8 motors and 12 servos. So I'll get into that a little bit later.
Oh, okay.
So yeah, why use servos? Weight. They're about half. Most of them are actually like I believe a motor is approximately 15 ounces, 14, maybe 12. Servos around most of these generally used servos are around 2 to 3 ounces. And so again, there's continuous rotation. So most regular servos are gonna stock servos that you see in the world are gonna have 180 degrees of rotation. But then the FTC servos will usually have up to around 270.
And this one has 360.
This one has, I'll get into, this is a special, the one that I'm holding right now is a special case. It's programmable. And so regular servos, again, can go into any position and they can aim for that. Continuous, you can't. But there's just a little table there. You're able to get servos with built-in encoders. You'll have to most likely get it somewhat custom from like the manufacturer. So I've talked to a few servo manufacturers. You're able to get a servo with an encoder, but it's a little bit more expensive. And yeah, that's basically it. And it's also hard to interface with, as you haven't really seen many teams use servos with encoders due to the fact that they're not really widely available. And the output on a servo it looks something like that. It has many different teeth, and it's called a spline. You'll see them plastic and metal. That one I believe is brass, but I'm not completely sure. And there's a link to servo spline input, which is most of the commonly used servo splines. There are two commonly used servo splines in FTC. There's the C1, which is 24-tooth spline, and then the H25/3F, H25T, or also known as 3F standard spline, which is 25-tooth. So on our team, we refer to them as 24-tooth spline and 25-tooth spline, but there are many different splines out there. And so what goes on a spline? So that's called a servo horn. So most servos come with a few cheap ones that are made out of plastic. And so they just screw in with the one screw onto the servo horn, or onto the servo spline. But there are clamping ones that exist, as I've seen on Amazon, but I haven't seen them used in FTC really. I've only seen clamping ones on Amazon. Yeah. And so those are just a few examples of what a servo horn would look like, where on one side you're going to see all of the teeth, but on the other side you're going to see a little groove for a hole. So there's the main servo we're going to use, and most teams use, is called a standard servo. And so they're generally use the same mounting, give or take maybe a millimeter or two. They're all essentially the same outer body, but they have many different specs. So some are going to be continuous rotation, some are going to be regular, and then some of them use metal gear, some use plastic, some are lighter, some are like heavier, some use steel, some use brass. There's all sorts of differences between them. And yeah, there's many different manufacturers that make these, because this is a really common part in also RC cars and also generally robotics, not just FTC. Standard servos you'll see used a lot. And then we have these dual mode standard servos, and so that's what I've just gave the demo with. And so they're all made by this, as far as I know, they're all made by the same manufacturer, which is VTech, and are all close to the same thing. And so they're able to change between a regular servo and a continuous rotation servo. And another thing you can do is you can program the limits for the edges of the regular servo, so that you don't have to do you don't have to program it like in Java or blocks figuring out what the limits are. You can just do that with the servo. And so the three models that, as far as I know, is there's the VTech FR5311M, which is the manufacturer version. VTech's the manufacturer. Then Rev was the original with their Smart Robot Servo, and then GoBuild a 2000 series dual mode servos. There's 25-1 and 25-2. So the version 1 uses not steel gears. Version 2 uses steel gears. So version 2 is stronger, but I'm fairly sure it's a little bit heavier. Got it? And so this thing that I have here, I just forgot, because you asked, this thing is called a Servo Programmer. And so it's used to switch the servo between regular, continuous, and program it. Yeah.
And that's how you program a servo, basically?
No, that's how you, it's essentially configuring. To program a servo, you'll do it in blocks, Java, you connect it up to the robot. That's essentially a servo configuration tool. So there's other servos. There's many specialty servos, which are unique. There are linear servos, which go linearly instead of rotary. There are nano to large servos. So you can see that HS40 in the top middle. That's a nano servo. Bottom left, you see that HS788HB. That is going to be a large servo. You can use this, I believe they use around the same spline, so you can use that for scale. Then there are many other different form factors.
Do you use linear servos?
No, we don't. So the main servos we'll use are these, and the next servo that we're getting into, which is the VEX 393 motor. So this counts as a servo in FTC when used with a motor controller 29, and I will show you what that is. And so it's more powerful than all the most standard size servos. It's continuous rotation, has a much different mounting pattern than the others, and the output shaft is a female square shaft, meaning that you have to put in your own VEX square shaft into it, and there's multiple gearbox options. There's high speed and regular. So you can see I have the VEX 393 motor right here, and then I have a connector, and then it's followed by a motor controller 29, which is essentially a 2-wire to 3-wire converter. So right there, that is going to be the whole wiring rig of the servo motor.
And why do you use the motor controller?
So it converts it into a 2-wire to 3-wire. So the VEX 393 motor uses a 2-wire output, because it's a DC motor. But then with the motor controller 29, you can control it with FTC hardware as a 3-wire servo motor.
Wait, and it uses the same voltage as a regular servo?
So it technically is supposed to operate off of 7.2 volts, but it can operate off of 6 volts.
Oh.
So it's all of its advertised specs are on 7.2, but it can operate off of 6.
Wait, so why did they decide to make this one late?
I believe it's because, so originally FTC was called First VEX Challenge, FVC, where you're only allowed to use VEX parts. And so what was happening, I believe, is these motors many teams had. I'm not completely sure. So they just made them legal so that teams would be able to use them.
I thought VEX was actually uncommon these days.
VEX is not common in FTC as much, except for these VEX servo motors, because they're more powerful than general servos. And so when choosing between a motor and a servo, it's a case-by-case basis. And so take into account the speed, the torque, the weight, the form factor, all the stuff you need, the output, the cost, as some servos can go into the range of hundreds. Most FTC motors are $30 or less. And the number of motors and servos you've used, because again, 8 motors, 12 servos. There's that limit.
So why would a servo be like $100?
They're really high quality servos. Very nice. But they can get very, very expensive. Okay. So now we have a chart here. And so this is a really big spec sheet where I have included, I had to trim this down. I have a link at the bottom for a spreadsheet with all of the motors, or most of them legal in FTC, and a few more servos. But you can take a look at the power, the ounce-inches rotations per second column, which is because watts is a little bit more complex unit. Power, that's just multiplying the rotations per second times the weight. That's just multiplying the rotations per second times the weight. So essentially what you're going to see is that the powers of the motors are fairly similar, except for the core hex motor. While even though they say that they're slightly different, and the GoBuild motors advertise a higher power, you're not really going to find much difference between the 3.7 to 1 Yellow Jacket and the Neverest Orbital 3.7. The main difference is that some manufacturers are going to advertise higher than others. But another thing you're going to see that's a little interesting is in GoBuild a Yellow Jacket. With the different gear ratios, you can see they have different powers.
The fastest one has the
So
most power.
that's because they're taking into account the gearbox efficiency. So that's something that it was really interesting when I made this chart.
Wait, so are these only motors or are there servos as well?
So the bottom 3 are actually servos. And so if you take a look at it, you're going to see the GoBuild a servo has about 300 ounce-inches rotations per second of power, while the Vex 393 motors, as they're called, have about 100 of that unit more.
So 400.
So they're a little bit more powerful.
For that power, I would have guessed that the 19.2 to 1 would have the most power, but no.
No, so power is multiplying rotations per RPM or rotation speed and torque
It does
together.
have the most power.
Yeah.
So when you take a look at the torque, so I have the stall torque, which is on the second to left column. So the stall torque is essentially how much torque is required to stall out the motor. So you don't want to be running at this much torque. So if you're running something that requires like 200 ounce-inches of torque, you don't want to run a motor with a stall torque of 200 ounce-inches. You want to run something we double, so we'll go 400 ounce-inches of torque at least. So that it's a lot, so that you run at like peak efficiency essentially, and there's no problems if the battery gets low.
Wait, what's power again?
Power is torque times speed is what I'm running at. That's the definition of power, and then I have a really weird unit I made on the right.
Right.
And if you take a look at the weight, you're going to see the gearbox, when you have a larger gear ratio for orbital motors, you can take a look at the GoBuild. They're much higher weights, just because they're a longer gearbox, more gears in there. But if you take a look at, if they're around 15 ounces, approximately. But then if you take a look at the core hex, that's 7 ounces, approximately. And a bare motor is 8.25 according to Rev. So if you want to get about half the weight, you'll go with the core hex motor just because of the weight.
How do you connect a servo, which is 7.2 volts, if the hub only provides 6 volts?
It'll work. You don't need to do anything.
But it won't be as fast.
Yeah, it won't be as fast. So the bottom I have some advertised at 7.2 volts. Nobody as far as I know has done testing on this, so I had to use the manufacturer's specifications. So these again do have inaccuracies, but if you take a look at the weights of them, the core hex is about half the weight of another DC motor, and the servos are approximately 2 to 3 ounces each, which is much lighter. So weight is a really important thing, just because if you put a motor at the end of a long arm, if it's a lighter motor, it's going to be a lot easier for you to rotate that arm than if it's a heavy motor.
So do the gearboxes make up a lot of the weight?
Yeah, they make up, from what this can see, the motor only, Rev HD Hex motor only, is 8.25 ounces. So gearboxes make up around half the weight, a little bit under from what this is saying, which can be understood. Yeah. So, does anybody want to take a look at this a little bit more? Or are you all good? I've gone through the main findings that I made when.
So does lower ratio tend to equal more power?
So that's because they're taking into account, theoretically it should have the same power, but then they're taking into account that the gearbox is much more inefficient if you have a higher ratio, because there's more gears that are spinning.
So why is the 188 to 1 and the 19.2 to 1 so similar?
Where's Orbital 20, you mean?
At the very top.
19.2 to 1?
And
I don't know, so that's just to go build a manufacturer spec. Okay. They all have a margin of error.
Okay.
And again, some manufacturers will market them as what their theoretical is supposed to be. For example, if you take a look at the Rev HD Hex Motors, without the gearbox and with the gearbox, it's approximately the same power. But GoBuild on the other end takes into account the gearboxes. And I've known some manufacturers will underrate their motors a little bit, so that if there's a bad motor because there's a good margin of error for how your motor performance. They'll rate them at the bottom of the 10% just in case, so that every team gets what they get.
Yeah.
And doesn't like get surprised when it doesn't perform. Yeah. All good?
Huh?
Okay. So now we're going to get into mounting. Servo mounting in general is fairly simple. You just use the 4 screws. The mounting pattern is generally the same. And the 3 most common FTC screw sizes, I know I'm not including quarter 20s, and those are pretty commonly used. A 6/32 M3 and M4 will most likely fit in all servos, all standard size servos. For the other sizes, I'm not really going into that, as that's more of a unique case. VEX 393 motors, you're going to probably have to make something custom to do that, just because of how weird it is. For motor mounting, there are 2 ways to mount a motor. There's clamping and there's face mounting. So, what the difference is face mounting is where you use the holes on the gearbox to mount the motor. You screw in screws to the gearbox. Clamping essentially takes a clamp onto the motor and clamps it in place. And so we're going to get into clamping. So the Tetrax parts for clamping, because we're going by building system now. So Tetrax has 1 and 2 piece motor mounts, and they allow the motor to rotate freely until tightened, and it only works for 37mm motors, which are in general the most common, except for like the GoBuild yellow jackets. And one thing about these clamping mounts, which is different, is if you have a spur gear motor, what's interesting is since the shaft is output, not from the center, it's offset, you can actually put a motor in a clamping mount and then rotate it to tension chain or make gears mesh.
Is 37mm the diameter?
Yeah.
Okay.
37mm is the diameter. Rev does not sell any clamping mounts.
Nice.
Yes, so Actibotics has 37mm and 32mm clamping mounts. They essentially look the same. So the main thing you're going to see is the one on the right, which is lighter than the Tetrax mounts. But they also have this one, the one on the bottom left, which is a swivel mount. I've never seen it been used before, but it exists.
What would it be used for?
I don't know. I don't really have a good use case for it, but I know it exists. It's not swerve.
Yeah.
And so GoBuild has essentially the same thing for 32 and 37mm motors. I'm fairly sure they have swivel mounts, but I'm not completely sure if they have them for both 32 and 37mm motors. And you can see they have many options. So Actibotics and GoBuild all have like a bunch of options. I'm only going over the most common are going to be those two, and I believe one of them's 32 and one of them's 37. But yeah, the most common is going to be those ones that are on the screen. Yeah, the most common is going to be the one in the top right and the one in the bottom left. Yeah. So face mounting, all motors except the GoBuild yellow jacket motors have M3 threads, and the yellow jacket motors have M4 threads.
That's the distance between.
So M4 is a thread type, so it's the diameter of the screw and how many threads there are per like inch, millimeter, per unit. But M3 and M4 are standard thread sizes. So for Tetrax face mounting, the core hex motor has a 16mm hole pattern, which can align with a Tetrax channel occasionally. Other than that, there's no Tetrax face mounting. Rev is all face mounting on the other hand. So Rev, we're going to first start off with the 37mm Spur gearbox motors. So they have these 2 bent and flat mounts, which are on the top right and right below that. You can see the bent and flat mounts. And so that goes with all of the general 37mm Spur gearbox motors, which is the NEVR-S, the Torquedo, and the 5201 series GoBuild motor. What's recommended when doing Rev is to double up the motor mount. So you can see in the bottom middle, there's actually a photo where you use both of the motor mounts. And that's a much stronger approach to face mounting the motor because you're using two pieces of metal and they're connecting to 2 sides of the Rev extrusion instead of just one. you can see that the black piece of plastic in the middle. It's called the HD Hex spacer. It allows use with all the core hex mounts, and it makes it easier to use the rev pattern that's on the HD Hex motor. So you can see in the bottom left there's a use case of that. You can see that. And again, when doubling, you're going to want to use both the bent and flat mounts. So you're going to want to use the slots on the motors. As they have holes and slots alternating, you have to use the slots. The holes don't line up. They have essentially the same thing for bent and flat mounts for orbital gear motors, except you're going to see with these the Spur gearbox motors, there's many different configurations you can place it in. So you're going to see, if you notice on the bottom, the right side of the screen, the flat mount, you can see that the hole pattern for the Spur gearbox motor is offset. It's not like completely centered, and that makes it compatible with the Rev building system a little bit better, and two of the common heights for motion. So there's two main common heights for Rev, and that makes it so that it's compatible with both of those heights. So Orbital, on the other hand, there's only one way you can output the shaft, and it works with, again, the Andy Mark orbitals and the Rev HD Hex orbital motors, which have that standard orbital hole pattern. And again, you should double because that makes it stronger. There's also Rev bare motor face mounting, which is, again, essentially the same. And Rev does sell some parts for bare motor, including a gear and some other metal gears to output from the bare motor, so you can make your own gearbox a lot easier. So now Core Hex motor. Core Hex motor has the 16mm diameter hole pattern, so it natively interfaces with basically every Rev part. It has, you can see at the bottom, slightly on the left, you can see that metal bent bracket, and that's, there's no flat version of that. That's called the core hex mount. It's a metal core hex mount. It's bent. And on the bottom left, you can actually see a use case of it. It's just a really strong core hex mount at one of the Rev heights, while most everything else is at the other height. Yes?
In the bottom left, it's a double mount, right?
No, so there is no double mount for this.
So that's not two?
So the second one you can see is actually a ball bearing plate,
Oh.
and that allows for your mount to actually be a little bit stronger. It reinforces the shaft.
Okay, so it's not like a flat plate.
Yeah, so you have the flat plate for the ball bearing and then the bent plate for mounting it in. And one of the strongest plastic plates that we like to use is the gearbox bracket. It's right next to to the right of the metal plate. You can see it has 3 holes. It's right there. And why we like this is because of the fact that it has those 90-degree, those triangles on the side, which make it less prone to bending. So it's a much stronger bracket than this motion bracket right here, which is flat. But you can actually double up on the motion bracket and the gearbox bracket. So you can do that to make it even stronger. Actibotics for the 37mm motors, all of them, they have a few different mounts. So you can see at the bottom left, they have motor mount B, which only 2 screws line up with the motor. And this is a really general motor. It works with motor mount, so it works with almost a bunch of different types of motors. So you get 2 screws that line up for spur gear motors, 2 screws that line up for orbital motors. And these were released a while ago, so this is what our team has the most, just because of how old they are and how many we have. But then there's also motor mount G and motor mount H, which are 2 newer ones. Motor mount G, which is to the right, allows for all of the screws to line up for a spur gearbox motor, which is all 6 screws. And motor mount H, which is on the bottom right, works for the orbital motors and allows all 4 screws to line up. So those are going to be better unless you need the use case of motor mount B. And there probably are a few other motor mounts that they sell, but I haven't seen them used before. There's the core hex motor face mounting for Actibotics, where they actually sell that core hex mount. It's just that plate for Actibotics. And then GoBuild, for the GoBuild Yellow Jacket motors, you just use an Actibotics to GoBuild adapter. And so I think the one I have pictured is the correct one. You can use that, and then it's compatible with the Actibotics hole pattern. It's really easy to interface with Actibotics. It just interfaces natively with the hole pattern. And now we're going to get into GoBuild for the 37mm motors, face mounting. Those are the two motors. They're essentially the GoBuild equivalent of the two Actibotics motors, as GoBuild and Actibotics are made by the same people. They're very similar. The one on the left is for Spur gear motors, and the one on the right is going to be for your orbital motors. For your 32mm orbital motors, the yellow jacket motors, that has the GoBuild pattern natively, so you just screw it in with an M4 screw and it works just fine. One thing that I realized I should mention for these GoBuild to Actibotics adapters is that they have the 632nd thread, so it essentially changes the face mount to a 632nd face mount.
So wait, the yellow jackets use a M30?
Yeah, they use an M4 thread, but then for the GoBuild to Actibotics converter essentially makes it the 632nd threads, because that's what Actibotics is built in.
Wait, but the Rev Core Hex motor isn't made by GoBuild.
Yeah,
so then
they still make it. So essentially, GoBuild, the parent company GoBuild, Robot Zone, has patents on basically every hole pattern they make. So they're able to make adapters for everything to work with their systems. Well, then since they have patents on it, all the makers of the other systems aren't able to really make adapters for GoBuild to like Rev, GoBuild to Tetrax. They can't make that because they have patents, as far as I know. So GoBuild and Actibotics by far have the greatest parts variety, because they just make so much and they're used more than just FTC really. So the core hex motor is really similar to what's in Actibotics. It just uses all 6 screws. And that's the recap for motor mounting. So Tetrax, again, uses mainly clamping mounts. Rev uses only face mounts. And Actibotics and GoBuild have everything. Yeah. And so there's some additional resources. There's also a bunch of links during the presentation that you should take a look at. And so thank you everybody for watching. Email Wizards.exe@gmail.com or comment in the description for questions.